Topology is very vast subject in mathematical science. Many people are facing problem to solve the question from topology. Now to learn about topology, we have to follow some books. The books are number 1, Topology by TB Singh. Number 2, Introduction of Topology by Munkresh, and you can follow also Kumersen. These are the books. Now for basic level of knowledge, you have to follow the book by TB Singh. He is a professor from Delhi University. And next, you may follow Munkresh for advanced level. This is for advanced level and this is for basic level. Right. So, let's start this topic. So, to study about topology, we need some knowledge about metric space. So, what is metric space? Suppose X be any non-empty set and D be a function from X cross X to real number R, and if it satisfies some property, number 1, D of xy is greater than or equal to 0 for all x comma y in X, and number 2, D of xy equal to 0 if and only if x equal to 0. Number 3, D of xy equal to D of yx, and property number 4, D of xy is less than or equal to D of xz plus D of zy for all x comma y comma z in capital X. Now, see here, for better understanding, suppose D is any distance function. Not necessarily it is a distance function. This distance function is one kind of metric space. So, suppose for simplicity D is a distance function. So, here if I take any 2 point x and y, and the distance between x and y is always either greater than 0, or if they coincide, then the distance between them equal to 0. So, number 1 is very easy. Number 2, the distance between x and y and the distance between y and x both are same. So, this is also an property for metric space. And number 3, if I take any 3 point, suppose x, y and z, then from childhood we know about the triangular inequality. Here the distance between any one length is less than or equal to the sum of other two lengths, and this is called the triangular inequality. This is called symmetricity. This is called equality. This is called non-negativity. So, these are the basic properties for metric space. If X is any non-empty set and D be any function from X cross X to R, and if D satisfies these 4 properties, then D is called metric. And X along with D is called metric space. Metric space, right? Suppose X is any non-empty set and D be its metric defined by D of xy equal to modulus of xy, then this is the distance function and this forms metric space. You can check it easily. I will show you. D of xy, that is modulus of xy, it is always greater than or equal to 0, right? Number 2, D of xy equal to 0 means modulus of xy equal to 0, that is x minus y equal to 0, right? So x equal to y and vice versa. Number 3, D of xy equal to modulus of x minus y equal to, if we take minus 1 common, then we will get, if we take minus 1 common, then we will get y minus x, and if we separate this, then we will get modulus of y minus x, which is equal to d of y minus y comma x. And number 4, it is the triangular inequality. We all know it from school level, right? You can write x minus y as x minus z plus z minus y, and by triangular inequality you can write this as this. So D forms a metric space and x comma D become metric space. Example number 2, if X is any Euclidean space of nth tuple and D be any metric defined on it by D comma x comma y equal to summation over I equal to 1 to n xi minus yi square. This is a metric on Rn. Another example, very important example is discrete topology. Suppose X is any non-empty set and D be its metric defined by D comma xy equal to 0 and 1. When 0? Whenever x equal to y, then it is 0, and when x not equal to y, it is 1. So it forms metric on X. You can prove this by yourself. Now proceeding further, what is open R ball? So open R ball means it is an collection of X such that the distance between X and A less than R, and it is denoted by B A comma R. It denotes open R ball and defined by this. Suppose if I take any point A here, where A is center and R is radius, right? Suppose A be any point and R be its radius, then all the point X which are inside this radius R, they form open R ball. Fine. In one dimensional, what we will get? In one dimensional, suppose it is a point, suppose A, then here we get A plus R and here we get A minus R. It is an open interval and it is general case, so we will get a ball. Now see, in one dimensional becomes an open interval, right? Now similarly, what is closed R ball? Similarly, it is denoted by B A comma R and B bar and defined by X, sorry, here it should be such that X such that D of X comma A less or equal to R, and if we draw picture, then we will get, if A is any point and R is its radius, now it can take the boundary point also since it is closed. Fine. Now continuity. See, in real analysis, what is the definition of continuity? If f is a function from A to say B, where A is any subset of real number R, right? Then for epsilon greater than 0, we will get delta greater than 0, and whenever modulus of x minus y less than delta, it will implies f of x minus f of y and its modulus is less than epsilon. Then when this condition satisfied, then we will say f is continuous, right? Now extending this definition in metric space, what we will get? F is a function from x to y, here x is any non-empty set and its matrix, we will denote its matrix by dx and the matrix of y denoted by y. Then see this, here x and y comes from A and fx and f of y comes from B. So we will extending this here. So when we take 2 points x and y from this x, then the metric will be d of x. So for epsilon greater than 0, we get delta greater than 0, and whenever d of x, it is a matrix, it is a metric, so dx of x comma y is less than delta, then d of small y, it is a metric on y, f of x comma f of y less than epsilon. This is the definition of continuity. Now what is open set? In real analysis, we know if x is any subset of R, then capital O is said to be open set if for any x in O we get an interval I containing X such that X belongs to I and I is subset of O. Then O is called open set. Basically, we all know another definition of open set. What is that? A set is called open set if all of its points are interior points. So basically, the X is interior point here, right? So we extend this definition in metric space. Suppose X is any non-empty set, no need that it will be set of real numbers. It is in general case. So X be any non-empty set, then U is said to be open if for any X in U we will get what we will get here. We get an interval, but in case of metric space we will get an open ball. X is the center. We will get an ball such that X belongs to BXR. It is obviously because X is the center and it is subset of U. Then U is called open set. See, X is any non-empty set, then U is said to be open, right? Suppose it is U, then U is said to be open if we take any point, say X here, and we will get an open ball entirely containing in U, then U is called open set, right? Now see some property of open sets. Number one, an open R ball is always an open R ball is always an open set, right? Why? Suppose it is an open R ball, X is the center and R be its radius, right? Then we can take any point Y other than X, then the distance between X and Y is always greater than or equal to 0. Say the distance between X and Y is R1 and distance between Y and the boundary will be R2. Then take minimum of R1, R2 and rename it as R dash. Then we always can find an open R ball with center at Y and radius is R dash. This Y is arbitrary, so we can take any point in this open R ball and we can make an open ball which is entirely containing in this previous R ball. So this open R ball is open set by the definition. Number 2, what is in case of real analysis, an open interval is open set, but open set may not interval. Why? This is the general case. So open interval is a particular case. So it is an open set, right? See here, if we take any interval, this is say a. So this is a minus suppose r, and this is a plus r. Then we can choose a point, arbitrary point b, and similarly we get an open interval which is entirely containing in the previous one. So the previous one is open set, but converse may not true. Why? Suppose this is real number, the set of real number, and if we take some disjoint open interval, and the union of this open interval and the union of these open intervals are open, but it is not an interval, because we know an interval is always connected, but here see they are disconnected. So it is not an interval. That is why open set may not be interval. It may be interval, it may not be interval. Here it not interval, and in that case it is interval, it is open. So number 3, phi and x, that is the whole space, are always open, right? Number 4, arbitrary union of open set is open. Finite intersection of open sets is, and again open. These three are very important. So this is for today's lecture. In next lecture we will start topology, and then these three play a big role to define topology. You can easily find the proof of these three statements in any standard books. You may follow the real analysis by S.K. Mappa, right? This is very good book according to me. I follow this book. You may also follow Munkresh, TB Singh, right? If you like my video, please do subscribe, like, share and comment. It will motivate me to upload more and more videos. So please do subscribe and share. If you have any problem, please do comment. I will try to solve your queries. Thank you for watching.